So in the past, we've seen that a function can be represented by a series. So all the way to 3, and then all the way to n, and then from n all the way to infinity. We've seen this. But let's say you want to truncate the series. Let's say you want to cut it right here. So from here all the way to n. Then this whole thing here. There, if you decided to cut the series, let's say here, then this whole thing here will then become your Taylor polynomial of order n. So of order n. So you can cut it anywhere you want. You can truncate it right here. Then this then becomes your polynomial, your Taylor polynomial of order 2. Or you can decide to cut it right here. You can decide to truncate it right here. Then this thing here then becomes your Taylor polynomial of order 3. So your function, this thing here goes all the way to infinity. Let's say you want to cut it here. Then this whole thing here becomes your Taylor polynomial of order n. But then if you look at this here, if you cut it here, you've still got this block. You've still got this block, and then you've still got lots of other blocks all the way to infinity. Well, so everything here becomes your Taylor polynomial of order n. But then this, you still got a remainder here. So you've still got this remainder here. You've still got this remainder here, and then you still got lots more remainder. But the clever thing about this is that you can squeeze all these remainders. You can squeeze all these remainders into one block. Now that's where you can squeeze all these remainders into one block. So squeeze everything. It's quite strange in that you're able to do that, because now it looks much neater. It's just one block. Your Taylor polynomial of order n plus another block. So it becomes a lot simpler. Your function is simply one block plus another block. But then if you look it up here, you've got your Taylor polynomial, and then you've got all these blocks here, and it goes on and on and on all the way to infinity. But the clever part is in being able to represent all these remaining blocks into one block. So all these can be squeezed into one block. That's where the clever part is. It's quite strange in that here you've got something to the power of n plus 1. Here you've got something to the power of n plus 2. Here you've got something to the power of n plus 3, and so on, all the way to infinity. But yet you can squeeze all these blocks into one neat block, but into one neat block, and this is to the power of n plus 1. But it's quite strange in that you've got something here, n plus 1, n plus 2, n plus 3, and so on. But yet you can squeeze all these into one elegant block. But the difference is that it is evaluated. Here you evaluated at A. Here you evaluated at A. But here you evaluated at some mystery point within our interval. And you've seen something like this before in the past. I will elaborate more on this, but what it's saying is that you can squeeze all these remaining blocks into one elegant block, But then it's evaluated at some mystery number C. And we've seen something similar to this. Remember Rowe's theorem here. We used to get the same concept. If you know f of a, let's say this a, b, if f of a equals 0 and f of b equals 0, then somewhere in between, that's our c here. We don't know precisely where c is, but we know it's somewhere in between. If this is 0 and this is 0, somewhere in between, the gradient must be 0. You see, the gradient is 0 here. The gradient is 0 here. No matter what your function may look like, if you know this is a 0, this is 0, then somewhere in between, there must exist a c somewhere in between where the gradient is 0. Look, C exists here. This is another C also exists here. Well, there must be at least one C where the gradient will be 0. No matter how you draw your function, somewhere in between there must exist at least one C where the gradient will be 0. And you've seen, so this thing here, we have in a way seen this before. There must exist a value C somewhere in between where this thing here will represent all our remainders, and also remember the mean value theorem. The mean value theorem. If you get this height, take away this height, which represents this height here. So this bit here represents a height, and then divided by this length here, which is b minus a. So that will then give you your average gradient. Well, somewhere in between a and b, there must exist a value c where the gradient, where the true gradient of the function equals the average gradient. So your average gradient looks like this. You see this point here, and so this is parallel to our average gradient. You see C exists here, and then also, so it's parallel here. So C here also exists here, because the true gradient at C is equal to our. The point here is that we've seen this in the past. We've seen Rolle's theorem in the past, and what this is saying is that there exists a value C where this thing here, we don't know precisely. We don't precisely know where C is, but we just know that it exists somewhere within our interval, where this block here can truly represent all the remaining block, all the remainders, all the way to infinity. So all these blocks here can be elegantly represented by one block, this block here. Okay.